All right, let's get started. So today we'll talk about data center networks. This is lecture 10, and this talk or this lecture is heavily adapted from Albert Greenberg's keynote talk in 2009. And before we talk about data center networks, let's do a quick recap of what we learned in the previous lecture. In previous lecture, we talked about operations at points of presence of POPs, and those are edge routing and reverse proxy. The Espresso, which is a system built by Google, pushes the edge routing tasks to edge servers, and that includes both the control and data plane tasks. And the results show that in some cases, these type of systems do much better than BGP. But in general, we talked about how hard is it to beat BGP. And now we will move our focus to data center networks. And to put things into perspective, earlier we talked about how different data center networks are connected to each other using networks like B4 or SWAN. In case of Microsoft, B4 is a network for Google. And then in the previous lecture, we talked about networks like B2, which were connecting the data center networks to the end clients or the end users. But today we will talk about how the data centers at a given location are interconnected, or the servers at a data center are interconnected with each other. The learning objectives for today's lecture are: what are the data centers in general? Like, what are the networking requirements? Why the previous generations were not able to satisfy these requirements? And we'll learn about what are modern data centers, or how are they designed, what are their building blocks, what are the underlying design principles, and what are the general lessons for us from these designs. So let's start with the first question. Data center networks are large facilities with tens of thousands of networked servers. There you have compute, storage, and networking all working in concert with each other. You can think of that as a huge warehouse scale computers, right? And as you can imagine, building these data centers is expensive. Really large data center, at least in around 2009, it used to take around $500 million to build one, right? You can imagine that's very costly. Now let's try to understand where these costs are coming from. So the table here is showing us the amortized cost of different components that we have in the data center networks. And note that these figures are from 2009, so they're reflecting how or what was the cost of building data center back in those days when we didn't have software-defined networking using, we were not using software-defined networking in those data centers. So the cost was mostly spent on servers, around 45%, which includes CPU, memory, disk. And then there were other components, power infrastructure, power draw were significant as well, a total of 40%. But as you can see, network, which includes switches, links, transits, etc., that cost around 15%. So it is small, but not insignificant. It is still a significant cost. And these numbers were derived from a paper that was published in around 2009 from Albert Greenberg, whose talk we are adapting here, and other folks at the Microsoft Research. So we saw that server cost is very high. Let's try to understand why the server cost is very high. One factor, or one key factor, is that the low utilization was considered good in those type of settings, right? So 30% utilization was supposed to be very good. And why 30% utilization? There were a couple of factors that explain why the operators were satisfied with just 30% utilization. One was the uneven application fit. So each server has these CPU, memory, and disk, but most applications were exhausting just one resource, and like others were just stranded at those CPUs, right? So in general, there was more of a one-to-one mappings between applications to CPUs. And that was not very effective because these applications were just exhausting one resource. Some applications were memory intensive, so they were just exhausting the memory resource, but the disk and the CPU were underutilized, right? So this type of uneven matching of applications to compute resources was one factor. Then the other factor was uncertainty in demand, that a demand for a new service can spike quickly, right? So to do that, or to handle that, there was a bit of a risk management, a bit of a defensive risk management that there were always spare servers left so that you can handle that excess spike in demands. So this does not sound like an ideal case and does not sound like how data centers are designed currently. The data center design goal is typically that we should have as much agility as possible, right? So the mapping should be any service should be mapped or can be mapped to any server in the data center, right? And in some sense, if you look at it from the abstraction perspective, what it translates to is that all these pool of servers should be translated into one single large fungible pool of resources, right? So that the services that are running on top of these servers can, in some sense, breathe. That is, they can dynamically expand and contract their footprint as needed. There are clear benefits if we can achieve this goal, this agility goal. One, it increases the service developer productivity. That if I'm a developer, I don't really have to worry about the lower level details about which server is going to run my application. Is that a good server to use or not, right? So all those overheads of programming can be avoided if we provide this single large fungible pool abstractions. The second is about the cost that, as we were discussing earlier, that this uneven application fit was one big factor that was contributing to underutilization of available resources. So if we can do a better job with that, then it will be possible to reduce the cost as well. And then the other challenges or the other benefit is that we can achieve high performance and reliability. So these are in general three motivations that you want to satisfy, or three goals that you want to satisfy for any infrastructure project. So how can we achieve this agility? Workload management, which means rapidly installing a service code on a different server. And if we have these virtual machines and disk images, I think this workload management is possible, and that's check mark that that is possible, that's feasible. We have the abstractions, we have the technology to do that. Storage management, providing means for a server to access persistent data across a pool of servers, right? So we have the abstraction of distributed file systems, blob stores, etc., and check mark for that. That's easy. What about the network? Here we need to provide means for communicating with other services, regardless of where they are in the data center. Like there should be no locality requirement about where the servers are, and we should be providing a seamless communication between all the servers in the data center. And that's something which was not doable back in those days. And that's something which was the, the billion-dollar problem that everybody was working on to figure out how can we provide the networking, the right networking abstraction for the data center networks. So let's try to understand or recall what the networking requirements are in this case. We want to provide developers a mental model where for them, all their servers and only their servers are plugged into an Ethernet switch, right? And this is a bit of a recurring theme that you have seen so far, that, in some cases, we call this as a big switch abstraction. In the case of SDX, we were calling this as the virtual switch abstraction, right? So there are two aspects to it. One is a big switch where you don't really care about the underlying topology. You just want an abstraction where all these servers are just one hop away from each other, right? The virtual part is that there can be multiple services or multiple tenants running in the data center network. So you should be caring about only the servers or service, only the servers that are running your services, right? So that virtualization, as virtualization is from two perspectives. One is the service level, the other is this topology, that there is just single hop, one hop, every service one hop away from each other. So in other words, the requirements can be categorized into three divisions. One is that we want a uniform high capacity, that the capacity between the servers should only be limited by their NICs, not the network, right? So network should not be the bottleneck for these servers. At whatever rate they can send the traffic out, they should be able to do that. And they should not be limited by the networks in terms of at what rate they can exchange traffic with the other servers. No need to consider topology when you're adding servers, right? So you should not be worried as a developer, you should not be worried about where you are going to add this new server for a service. And we want performance isolation, right? So this is related to this virtual abstraction that we were talking about, that you should, as a developer, you should not be worried about who all, like what are the other services running in the network, what type of application patterns or like data traffic patterns they have, and what type of patterns I have. Do I need to modulate my behavior based on the other services that are running in the network, right? So in general, as a developer, we want this performance isolation app guarantees that, traffic of one service should be unaffected by the others. And the layer 2 semantics is basically the big switch abstraction that we were talking about. The addressing should be completely flat. Any server can have any IP address. The IP address should not be tied to the location of where the server is located. The server configuration is the same as in a LAN, local area network, and the legacy application that are depending on broadcast just must work as is. So we have seen these requirements in other networks as well. I think especially if you remember the Nisira related project that we were paper that we were reading, I think these type of requirements were in that setup as well, because those are multi-tenant data centers, which are very similar to how we have the data center networks for companies like Microsoft, or Google, or Facebook. So now let's try to see whether the previous generation of data center networks were satisfying those requirements or not, right? So to understand that, let's try to understand the architecture that was used. You can, the data centers were basically one big layer 2 pool, right? So all the S are the layer 2 switches, and A are basically the rack of servers with a top of rack switch, right? So they're you have a rack of servers. All these servers are connected to the top of the rack switch, and then this top of the rack switch is connected with the S switches or aggregation switches in the data center network. And then all these these switches were connected, there was a hierarchy of these switches, and then the top level hierarchy of S switch was connected to the L3 access router or AR, right? And that is the layer 3 part of the network in the data center. And then these AR or the access routers were connected to a core router of the provider, or whoever is the service provider here. So the core router of that, think of if this is something which is built for Google, so Google will have some core router which will be connected to the AR router, right? And then those core routers can talk to each other over internet. And as we just to provide some context, as we read about the B4, so in B4 they have the option of connecting one data center with with the other using the public internet, but then they chose to build their own wide area network, and that's what B4 is all about, right? So this is even an older version of how data center networks were designed or viewed at that point of time. And there was a paper from Yahoo that came out around 2008, 2009, which actually talked about this architecture in more details, and talked about what volume of traffic is going through the public internet when one data center is talking to the other data center. So clearly, this type of architecture was a bit hierarchical in nature, which is a very natural thing to have. The redundancy factor was one, every top of rack switch was connected to two different aggregation switches, and equipment higher in the hierarchy were handling more traffic, right? So there were fewer devices up at the top, and then they were handling more and more traffic. So they were more expensive, and more efforts were required to make them increase their availability. So the design was a bit scale up design, right? So there was complexity was pushed up in the hierarchy of these switches. And the servers were basically connected via 1 Gbps link to the top of the rack switches. And there was, in some sense, a bit of an oversubscription that, if there are 20 plus servers that are connected to top rack with 1 Gbps link, so we're talking about 20 Gbps links, but the links from the top of rack switch to the S was maybe 1G or 10G. So there was a bit of an oversubscription at that part, right? We'll cover the oversubscription part later as well. So this is the architecture of the data center networks, before the new generation of data center networks came out. And that was, as you can see, is looking at the architecture, you can sense what type of problems it will have, but we'll try to dig in those problems in more details now. So there's First problem is about this internal fragmentation that is going on, which is preventing application from dynamically growing or shrinking. And as we discussed earlier, that this is very critical for the agility that we require in the data center networks, that the applications should have this, single fungible pool of resource abstraction, right? Which means that they can use whichever server they want in the network or in the data center network for their applications, right? And if say I want to use any server in this type of network, there are going to be challenges, and that is creating that internal fragmentation, which is preventing applications from dynamically growing or shrinking. So let's look into this figure. The color schemes are telling you which type of services are using those servers. So green color is one type of service, the violet color is another type of service, right? And then the virtual LANs or VLANs are used to isolate, to provide some isolation between the traffic that belongs to application type 1 or service type 1, or green versus service type violet, right, or purple. And then the IP addresses are topologically determined by the ARs, which were the access routers. So, whichever set of servers are connected to those ARs, they have the IP addresses assigned based on that. And then if you want to, add more servers to a particular service, then you have to do a lot of reconfiguration of the IP addresses and the VLAN trunks, which is, painful in a sense that, it is a lot of work. It is prone to errors. It is slow and often manual, right? So these are all the things that you don't want in a network, right? Like your transition, your ability to add a new server to a service should be very seamless, right? It should not require a lot of manual intervention. It should be as less error prone as possible, right? Now, if I want to add a new server to this green service, which is in a bit a different layer 3 domain, then that will require a lot of reconfigurations in the network to make it work, right? So it will require changing the IP address of the server. It will require changing the VLAN trunks. It will require adding new routing entries at the top of the hierarchy switches, like the AR switches and CR switches, CR routers and AR routers, to make sure that these servers can communicate with each other in a seamless fashion, which is very problematic. So this in some sense, this complexity was pushing that, the applications are, not leveraging this agility, right? So they're just limiting or localizing the type of servers that they can use, because going beyond the local set of server pools is, prone to errors. It's slow, and it requires a lot of changes in the network, right? So it's not as seamless as you want, and it's undesired. And there was no performance isolation as well, right? Because of the nature of the links or the structure that we have here in this traditional topology. If one set of services are sending a lot of traffic to the internet, then that is going to affect the other set of services, right? So in this example, suppose that the purple service is sending a lot of traffic upstream to the internet, right? And because the green one and the purple one are sharing the same set of upstream devices, and there is an oversubscription of resources. So if one is using a lot of those resources, then the purple one is using a lot of those resources, and the green one is going to suffer, right? So there is a collateral damage because there is a shared fate between the resources or the switches that are used by different applications, and there's an oversubscription in the network. And more importantly, I think if we want to use servers that are at a different location, then you are so in this case, if you want to provide server to server capacity at a location which is not local to an individual set of server, then there are different challenges that the network has to handle, right? So as we discussed in the previous lectures as well, that the data center are running two types of applications. One are the outward facing, which are communicating with the users. The others are the internal computations, right? And those internal computations require a lot of high server to server capacity. But if the server to server capacity is limited by the network, that is forcing localization of these servers that you can use for applications, and that severely affects the agility that these data center networks can provide. So typically the oversubscription rate, what is an oversubscription rate, right? So if you have, say, server rack with 20 servers, each of them have 1 Gbps link. So that translates to 20 Gbps, like max transfer that the top of the rack switch might require. But if that top of the rack switch is only connected to 2 different links and each of them have a capacity of 1 Gbps, so the max capacity that this top of rack switch can support is 2 Gbps, right? So the max requirement can be 20 Gbps and the max support can be 2 Gbps. So this is what oversubscription ratio or oversubscription is called, that, peak demand to peak resources ratio is called the oversubscription ratio. And that is a, a good metric to understand that in worst case, what your, how much, what is the worst case scenario where your network will become the bottleneck, right? Like if all the servers are trying to, communicate with a server which is, in a different pod, then this oversubscription structure that we have in the network is going to make network a bottleneck, right? Like this is the worst case, but even if the servers are trying to send 4 Gbps of traffic and it can only support 2 Gbps, there is already a oversubscription in place, and that's going to result in degraded performance for all these services here. So there is no way we can sustain anything beyond 2 Gbps of communication between servers in 2 different pods here. So in general, networks need a greater bisection bandwidth, right? And they require traffic, and currently they require traffic engineering to use what it has. So when we say that they require a greater bisection bandwidth, it means that, if they're trying to communicate with servers in a different layer 2 pool, then we need really high bandwidth at the top hierarchy to enable that type of communication. If you, given that there are these differences in terms of demands that will, or the dynamism that is there in the demands, then you might have to do traffic engineering. Given that you have limited resources and more demand, then you have to do very clever traffic engineering to make the best use of limited resources that you have, right? But the dynamic reassignments of servers, especially given the map-reduced style computations, it means that the traffic matrix is constantly changing, right? Like the demand patterns between different type of servers and applications, given that their requirements are changing very rapidly, the traffic matrix, which is typically an input for any traffic engineering decision making, is constantly changing, right? So to make good traffic engineering decision, you need to know what is the demand, right? But if the demand is constantly changing, then that means that efficient decision or good decisions are also required to change very frequently, right? And that is not something which the typical traffic engineering solutions are designed for, right? So when we were looking at the traffic engineering solutions for SWAN and other type of solutions, or before, then they were looking at these demands at the order of 5-minute granularity. And then they were looking at those aggregate demands because they were providing this aggregate capacity between different data centers. So in those cases, that was fine. But I think if you're trying to provide it dynamic reassignment of things at the server level granularity, then the traffic matrix is very, very dynamic. And this is something where the traffic engineering solutions are not able to handle. And there is another problem with the faults, that the networks, especially the ones, the components, the network components, especially at the top, need to be very reliable, right? And that's something which is very hard to achieve. In general, you can always assume that any component has some probability of failing, right? So things will fail. It is really hard to ensure that there is going to be no failure at all, whether it's a hardware failure or a software failure, right? So if you want to make networks very reliable, then given this hierarchy of this topology that existed, it was very top heavy, which means that if something very small, even a small failure at the top for the top level routers is going to affect almost all the servers that are downstream, right? So if one AR router goes down, or if one CR router goes down, that's going to take all the servers off the network for a very long period of time, depending on how long the problem is. So this was not a desirable situation to be in, because these data center networks are very vulnerable to, like very low frequency or low probability of failures for the upstream devices, right? So that's not a design that you want to, embrace for building data center networks. That's something which is very vulnerable to failures which are inevitable. So far we talked about, what are the data center networks, what are the requirements, why the previous generations of data centers were not able to satisfy these requirements. Now we're going to talk about a new or a modern data center design. How are they built? What are the building blocks? What are the design principles? And what are the lessons for us from these data center networks? So the building blocks, if you talk about building blocks, switch on chip ASICs was something which is very popular in the data center networks. It has been embraced. Unlike the conventional, like layer 2 switches, or like the switches that were used or designed by companies like Cisco or Juniper, these are very cheap. These are commodity switches, and like the cheapness of their their benefits are coming from the fact that they require relatively low buffer sizes, packet buffers, and the technology is also evolving, so they were able to support like 24 1G ports, or like 4 10G ports. The number of forwarding entries, unlike the conventional routers, if we think of, is relatively low, right? Because the decisions that these switches have to make are heavily localized, so they don't have to keep the entire IP prefixes for the entire internet in their TCAMs, right? So they can work with smaller TCAMs, they can work with smaller packet buffers that helps reduce the cost, right? And in general, the trend, like even then and even now, is that the port density is increasing, the capacity of a single port for these switches is increasing. It's getting cheaper and cheaper over time, right? But if that is the trend, I think the design has to be something which is able to leverage these properties of the switches. The other thing that is very important to understand from data center network perspective is that the propagation delay is not really a concern, right? So when we think of networking from the internet perspective, and if you're trying to send the traffic from one part of the world to the other, it's hundreds of milliseconds of time that it can take, and that's a lot of it is contributed because of the propagation delay. But in data center networks, all these servers are physically close to each other, so propagation delay is, you can kind of like ignore that, right? So trying to dig a bit more into it, the end-to-end latency for a particular packet in the data center network comes from two things. Because we can ignore propagation delay, so we can ignore that. So there are two things, which is switching latency and the queuing latency, right? So if you are switching from 10G to 10G, so it kind of like approximately takes around 2.5 microseconds, right? And queuing latency depends on the size of the queue and the load that you have on the network. But typically, in a quiet data center, it takes around 10 to 20 microseconds for a packet to go from one server to the other. And but in the worst case, which was measured from the data testbed built at Microsoft, with all-to-all traffic pounding at a link utilization of 86%, was around 2 to 8 milliseconds. That's kind of like the worst case latency that you can see or expect in a data center network. Now, compared to the time it takes for a packet to get processed in a host network stack, which is around 10 microseconds, that's a relatively small time period, right? So for application developer SLAs are typically greater than 1 millisecond. So the latency is not really a bit of a concern, right? So what that means is that when we were designing these conventional networking routing protocols, one of the factors that was always of prime importance was to make sure that the packets are going through the shortest path, right? And the argument there was that the shortest path basically are translating to a lower propagation delay. But in data center networks, as we see that the propagation delay is kind of like negligible. So even if I can bounce the packet to some path which is relatively long, which wouldn't be considered as a good path in a conventional network, but in the data center networks, that's still a good choice, because propagation delay does not add much. There are some queuing and switching latencies, but they are also very negligible compared to the time it takes for a packet to get processed in a network stack anyways, right? So this gives a bit of a flexibility in terms of what type of routing paths one can use in data center networks to direct or to send traffic from one server to the other. And there was an extensive study done to characterize the data center traffic, and there were results that were very different and surprising, right? I mean, they were intuitive, but they were very different from what people had, or what basic assumptions people work with when they were designing networks, right? So to this type of study, the folks at Microsoft conducted a large study where they instrumented a large cluster using data mining, like the applications for using data mining, and then they tried to identify distinctive traffic patterns. So there are two takeaways from that study. One, that the traffic patterns are highly volatile, right? And this is something that we were discussing earlier as well, that like you have these type of map reduce applications. There is a lot of volatility in terms of the demands that are there between access, like the data transfer that is going on between multiple servers, right? So there are large number of distinct patterns even in one day, right? So you can't really cluster them into, okay, this is pattern one, this is pattern two, and there are only two patterns that you will see in the entire network, right? During a day, there are so many different type of patterns that will come out depending on what type of application is running, what type of like input is coming in. So this is very different from how things were in the past, because in the past, when you look at the inter-domain traffic or access, like the communication between two different ASs, there was a lot of predictability in the traffic, and there were a lot of papers written on this topic of predictable traffic matrices. And because the traffic matrices were predictable, so that made traffic engineering relatively easy thing to do, because relatively easy. Like, I'm not saying traffic engineering is easy, but if the demands of the traffic matrices are a bit more predictable, then you can actually develop reasonably efficient traffic engineering solutions. But if the demand of the traffic patterns are highly volatile, it is really hard to design good, effective, or efficient traffic engineering solutions here. So one fundamental thing to understand here is that why am I talking about traffic engineering in this context, right? So traffic engineering is good if you want to make efficient use of limited resources, right? So if you have a limited set of resources, if you have diverse set of demands, but they are relatively predictable, then you can make decisions about how you should send the traffic over these limited set of network resources, right? Such that you are making the best use of those resources. But if the demand is so predictable or like unpredictable or highly volatile, then you won't be able to make effective traffic engineering decisions, right? So what that actually translates to is that there is no way you can make this work with fewer resources. So a takeaway here is that you have to come up with a design which is not limited in terms of resources available, because there's no way you can do a good job with traffic engineering here, right? So you will technically need more resources to handle this type of traffic pattern. And the other thing is also that traffic patterns are highly unpredictable, right? So there's which kind of adds to the point that I was making earlier, that it is volatile, but it is also unpredictable, right? So it's really hard. It depends on what type of behavior user has exhibited, and what type of computation that is triggering, and then based on that computation, what is the nature of that computation, how many servers need to be added to this compute task and stuff like that. So based on those reasons, there is a lot of unpredictability in terms of the traffic that is being exchanged between different servers. And we will see how this observation actually motivates the design of a new generation of data center networks. But one takeaway which is clear here is that traffic-aware optimization, which was very common for the networks before, like the wide area networks and other type of networks. If you want to do that, then it needs to be done frequently and it needs to be done rapidly, which is non-trivial thing to do. But what are the opportunities in data center networks compared to the other networks that we talked about earlier? Data center controller knows everything about the host, right? Because it has full control over the host, right? Like it is not tied to this fact that when we talk about the inter-domain network, you only control one part of the network, and then once the network leaves your leaves your administrative domain, then you don't control the packets at all, right? But or you don't control the end host as well. But in data center case, you control the entire network, you control all sets of hosts, right? So that's an opportunity. Uh, and also the host OSs are easily customizables, right? So if I want to write a new driver, new program, and if I control all the hosts which are going to communicate with each other, that gives me a lot of flexibility in terms of the changes that I can make, right? Because the host OSs are basically user, like you can write different types of user space programs and stuff. So, like making changes, making them customized to your network requirements is relatively easy, which is not the case, right? Like if I am trying to build something for the inter-domain network, I cannot expect to change the like programs for each and every device that is accessing my service, right? So if I'm trying to build a website and other people are trying to access my website, so in that case, if I have this public facing part of the network, I don't control all the end hosts for this like the links or the flows between the servers and the clients, right? So that like if I want to come up with a solution where I need to customize the end host, that's not going to happen, right? But that's not the case in data center networks. In data center networks, you control the source, you control the destination, and you can customize the things whatever way you want. The other opportunity is that if you rather than making these intelligent traffic engineering decisions, if you just randomly distribute the flows across multiple links, it can work because there are a lot of flows and most of them are like medium-sized flows. None of them are elephant flows, right? We'll get to this point in more details soon. And then the other reason why this type of approach can work is that the commodity switch-to-switch links are substantially thicker or have higher capacity than the maximum thickness of a flow, right? So this is also these observations are coming also from a measurement study where they observe that unlike the conventional networks or think about the wide area networks, the inter-domain networks, the flows that we see in the data center networks are too many, right? There are too many flows which are relatively short-lived and they're not very huge. That is they're in abundance in the data center networks, right? And you might be wondering what elephant flow is. So elephant flow is something called as you can call it elephant or a heavy hitter, and these are the flows that are exchanging a lot of traffic, right? So if you look at the data traffic distribution for, say, for example, whatever traffic is coming in and out of UCSB, we will notice that there are most of the flows are similar to what is being reported for the data center networks, but then there are significant fraction of flows that are elephant flows that are transferring a huge amount of data, and they are also contributing significantly to the total requirements or total usage of the network, right? So think about, say, some big data transfers going on for a physics application, right? So you can think of that as an elephant flow. You're transferring terabytes of data with just one 5-tuple flow, right? So that is one example. That's something which you don't really or typically observe in the data center networks. So which means that there are too many new flows coming in and you can make independent decisions for each of them because you know that they are not going to last very long. So even if you make a bad decision, you know that over time those flows will end up soon anyways. So you're not getting stuck with those bad choices, right? So you're free to make those type of probabilistic decisions, and you don't have to make those complicated traffic engineering decisions here. So all these observations are telling us that it is possible to make data center networks which are much simpler than the way they were designed earlier, right? The kind of architecture that we saw earlier, it is possible to design something which is much simpler than that. So how can we leverage these type of observations? So VL2 was a system that was designed by Microsoft around 2008-2009 time period, and it was basically leveraging a bunch of design principles that were derived from the opportunities that we have from the observations about the latency, about the switches that we have, about the traffic patterns that we have in the data center network, right? So the key design principles for VL2 were that it believed, or it argued, that it makes sense to randomize the traffic so that you can cope with the volatility of the traffic, right? Because there is tremendous variability in the traffic matrices, so it makes sense to randomize the decision about where a particular flow should be forwarded to, right? Or like, which next hop it should be going to. It also argues that, like we should separate the names or IP addresses assigned to a particular server from the location where it is, right? And that will enable us to let any server be used for any service, or like the agility goals that we had for the data center networks. The third principle is that it is embracing the end system. So it argues, which is fair as well, that like the end servers that you have are already designed to do some certain type of computations. They are much more programmable than the switches or the network devices that you have in there. So you should be able to, when you're designing these data center networks, you should be thinking about leveraging that flexible programmability that the end systems are offering. And this is also very unique because, as we were discussing earlier, the data centers are the only type of network where we control both end hosts, right? Both, we control the source and destination both, right? So we can leverage their programmability in ways that we can simplify or like avoid or offload the complexity from these switches and offload some of that complexity to these servers. And the fourth principle that it was built on, and like this is a bit of an evolving thing, but it argued that it is possible to build these interesting networks, or like the next generation of data center networks, with the devices and switches that are already existing, right? So you don't have to build something new. They were basically arguing that with whatever is available right now, the merchant silicon ASICs, or which are low power, low cost, you can actually build all these systems using those devices. So these are, like the distinguishing design principles for the VL2 system that was proposed by Microsoft. The key enabler, which we discussed briefly earlier as well, is that you have programmable switches with high port density, right? So which means few switches with high port density can be used to build these type of networks. These switches are fast, cheap, and flexible. So they are fast because you have the ASIC switches on a chip, and they're cheap because the small buffers, small forwarding tables, things that we were discussing earlier. And then they're flexible because they can be programmed, because the control plane is programmable, and that can be programmed like separately. So the data plane control plane separation that we were talking about, the control plane is programmable here, right? Which is a desired aspect. And then, of course, like similar to the SDN principles that we learned earlier, this flexibility of this programmability enables centralized coordination. We can scale out data center networks, unlike the enterprise networks. The centralized services already control, monitor health. So like some of these points are a bit old. So take it with a grain of salt here. But like all these ideas that were there in 2009, that it is possible to enable centralized coordination for these dumb switches that are sitting in the network, right? And 4D is a paper that we discussed very briefly in the earlier part of this class, which was one of its first type of paper which argued that like how we can have this management layer which enables centralized coordination for devices on a network. So this is the topology that was embraced in the data center network, which like as we will see that like is made a lot of sense. It helped satisfy different requirements that we had for the data center networks. So class topology is the one where like we have all these interconnected switches. We avoid any type of oversubscription in the network, right? So typically the way you can look at it is that you have these multiple switches. All these switches are alike, so you don't have to differentiate between at which level of hierarchy in the network what type of switches can be deployed or need to be deployed, right? So all the switches are almost same, right? Irrespective of whichever level of hierarchy they are operating in. All of them have d number of ports, right? So as you can see, the top layer has D ports. The intermediate layer also has D ports. The top layer is using all these D ports to connect to the aggregation switches, right? And it is connecting to all the aggregation switches. So it has D ports. Then you can think of that there are D aggregation switches, right? And because like each of the aggregation switches is only using D/2 ports to connect with the intermediate node switches. then only D by 2 number of switches are required at that level of hierarchy, right? So at the top, you have D by 2 switches. They are connected to the aggregation, the second layer, and the second layer is using half the ports to communicate with the top switches and half the ports to communicate with the downstream switches, so the half for upstream switches, half for downstream switches. In total, all of these switches, like the aggregation switch or the intermediate node switch, they are all having D number of ports, right? So now you can actually, as we were talking earlier, that there is a trend that the number of ports that you have on a switch are increasing, but depending on how many ports you have on a switch, you can actually dictate that what will be the number of servers that you can have in a pool, right? So if your switch has a node degree of 4, then you can afford to have 80 servers in that pool. If the node degree is 24, then you can afford to have around 3,000 servers in the pool. And if that number goes to something as high as 144, then you can have around 100,000 servers in the pool, right? So this was a simple, topology. This class topology was designed sometime, I believe, in 60s for the circuit switching, for the telephone lines and stuff. So that this topology was very successful, very prevalent back then. And then this was used to design the fabric inside the switch itself to make sure that you have non-blocking lines. And then eventually this kind of came out of switch to dictate how the data center network should be designed such that you can have non-blocking communication. Well, the unique properties about the class topology is that it is a bit of a scale out design, not a scale up design, which was the case for the previous generation. The bisection capacity at each layer is the same, right? So there is no oversubscription in this type of environment, right? So if you have, say, top of rack switch, which is connected to two 10G with two 10G links to the aggregation switches, and then it has 20 ports of 1 Gbps link to the servers, then 20 Gbps is the max requirement and 20 Gbps is the max support or max bandwidth that it can support. So the oversubscription ratio is 1:1, which means that there is no oversubscription in this case, right? So in other words, if I simply say that this class topology is basically leveraging this additional port density that was available in the switches, and class topology made perfect sense. It was adding all this, it was leveraging this additional port density to add more and more links between the switches to make sure that the oversubscription rate is as low as possible, right? And that is enabling us to not have any type of oversubscription. And also, even if there are some links that are failing, which is very common, expected, the degradation is much more graceful, right? Because there are so many other options that a particular switch has to transfer or to forward the packet to. And what it does is that it uses randomization to cope with volatility, right? So because we can't really predict how the traffic patterns are going to be in the future. So rather than deciding a smart traffic engineering decision about which path a particular flow should be taking, it just makes a random decision, right? So every hop is making a random decision. Like say in this case, it has when the traffic goes from the top of rack switch to the aggregation switch has D by 2 different options at its disposal. It can just randomly map a particular flow to any of those switches, right? And because there's full connectivity across all the switches, then traffic can still reach it. The downside of it can be that it might require the downside can be that for temporarily you might have more switches assigned to a path with you have more flows that are assigned to just one path, because there is still a probability that all of these flows can get mapped to one link, right? But because these flows are relatively small in duration, so there might be some temporary issues or temporary congestion issues that we can see in the network, but the probability of such events happening is relatively low. And the probability of such a congestion event to persist for a very long period of time is even smaller, right? Because these flows are small. So even if you make a bad decision for a certain flow, that decision will amortize over time because those flows don't last for a very long period of time. So variant load balancing is the approach that basically is, the instantiation of this randomization approach. that every flow is bounced to a random intermediate switch, right? And this is probably hotspot free for any admissible traffic metrics. It doesn't matter what is the traffic pattern here. This is probably hotspot free approach. And if there are cases where you have, like really long flows between servers, then the server can choose to like break these long flows into smaller flowlets and make those randomized decisions for those flowlets as well. So the other design goal was also to separate names from locations, right? So the approach here is that the design is leveraging the programmability of the switches or of the servers that are at the end and at the edge, and then like keeping things as simple as possible for the intermediate switches, right? So what it does is that basically we have discussed this in previous lectures as well. It is kind of like enabling source routing here, right? So the decision about how exactly what type of path, which is still random, should be taken by the packet, all that decision is made at the source itself, right? And then it encapsulates the corresponding headers. So this makes things very, very easy for the intermediate switches, right? All they have to do is to look at these headers, which have the decision already encoded ahead of time. So they will just look at these headers and then make the forwarding decisions based on that. This simplifies the amount of forwarding state that these switches have to maintain, right? And also it kind of like given this randomization that is going on, then the probability that a particular switch will get too many packets at any point of time is relatively low, which means that they can work with smaller buffers, right? And this goes well with the type of technology that was available out there for building cheaper switch. The only factors that were contributing to high cost for a switch were the ones that required building a huge buffer for these switches and also required maintaining a lot of TCAMs in the switch, right? So now you don't require a lot of TCAMs, you don't require large packet buffers. So these switches can be much, much cheaper. The only thing that you need is to build switches that have high port density, right? So that you can support more and more servers. So this is the prototype of VL2 that was designed by Microsoft. And this is 2009 time. These type of things were new, and in practice and like in theory, all this makes a lot of sense. But you still need to demonstrate that this is still a good idea and this can actually scale, or this type of system is exhibiting or is in compliance with what theory says that it should do, right? So coming up with some theoretical solution is one thing, but like demonstrating with some experimentation that actually worked is another. And we'll talk about how Microsoft used this prototype to demonstrate that all the theoretical ideas that VL2 was talking about are actually possible in the real world. So one, goal was that it should be able to achieve uniformly high throughput, right? So what they did was that they set up an experiment where there was all-to-all shuffle, like all servers were communicating to each other and they were shuffling a data of around 500 megabytes among the 75 servers that they had in the test bed, right? And this was an excellent metric of overall efficiency to demonstrate that like whatever is the best possible, is it able to achieve that or not? And the results were pretty good, that the average good put that it was able to achieve was around 58.6, which was very fair. So fairness is basically telling you that like there is isolation between different type of flows, and the average link utilization was around 86%, which was much, much higher than what was the standard practice in data center networks back then. And there are different metrics that they came up, the theoretical metrics about, okay, theoretically what should be the efficiency of such a network and how efficient or inefficient this solution is. Then they quantified it, and they quantified that VL2 is actually 94% of the efficiency is 94% of the optimal, which is a very, very good result, right? I mean, optimal is theoretically best where where you can make all these complex computational decisions on the fly. But in practice, making all those decisions is very, very expensive. But being able to just make those random decisions, right? Like just flipping a coin and sending a flow to one of the intermediate switch that you have as an option, and then still being able to achieve 94% of the optimal result is an incredible result to have, right? So, I think that I didn't explain this graph, so I should make an attempt to make sure that you understand what this result is all about. The experiment, as we talked about earlier, is an all-to-all shuffle, right? So you have these 75 servers. They're doing all, like every server is talking to every other server, and it is doing a data transfer of 500 megabytes, right? And then this experiment is running for around 300 plus seconds. And as you can see, so the number of active flows is basically how many 500 megabyte transfer is going on. So, like it will take some time for like the number of active flows to increase. That is indicated by the green line. And you can see that it peaks quickly around 30 seconds or something. So it takes around 30 seconds for all of those flows to kind of like, get active. And then you can see that the throughput is very high. I mean, like, it starts with a very high value, but then it goes down a bit. So that's where, like all these other flows are getting active. So it is like maybe 60 plus is the optimal that is possible, but then like it is going to a relatively lower number, but then it stabilizes at that, right? And then it is able to achieve that around 58.6 Gbps average good put for this entire duration, right? And then the flows, as the number of active flows go down, then over time the good put also goes down because they're done transferring all that data. Okay, so this result is clearly demonstrating that VL2 is very efficient. It is able to achieve 94% of whatever was possible with an optimal decision making here about sending which path or which set of router, which set of switches to use for sending an individual flow. If you have a very complex computational tool in place, and all these metrics about the traffic demand, so you can make those decisions at the granularity of every flow. That's computationally very, very expensive, but assuming that you can do that, then that will be the optimal solution. And VL2 was 94% of that optimal solution. That is incredibly awesome result to have. The second is about demonstrating that VL2 is providing performance isolation. And that's something that we discussed earlier, that like if the requirements for a particular service increases, that should not determine the performance of the other part of the network, right? So this experiment is actually demonstrating that. These are kind of like two set of experiments where you have service 2, like service 1 is running, and then all of a sudden you increase the good put for service 2. And as you can see that, it can sustain a higher good put for the service 2, but it has zero impact on service 1, right? So that is the the performance isolation. And there's another experiment that they did where they were like starting mice flows, which were mice meaning short flows. So they were starting these very short duration high good put high good put flows. And basically the green line is telling you the number of mice flows that were started. So these are all short duration high data transfer that's going on, but they would cumulatively large number of mice flows were started. But as you can see that the aggregate good put is almost the same in this case as well, right? So these are two type of experiments where either you persistently increase the volume of traffic that is transferred by service 2, and it has zero impact on the service 1, or you add a lot of small flows in the network and keep on increasing the number of those flows that you're adding, and it has zero impact on the other service or the aggregate good put, right? So this demonstrates that this design was able to achieve the performance isolation that was desired. And the other point is that it is resilient to link failures, that as we expect that, whenever there are link failures, then the transition should be graceful, right? So if a link goes down, then it will be able to the performance will degrade, right? Because you have one less link to work with. But it should the performance should not be completely abrupt. So in this case, what they're doing is that they're taking one link out at a time, right? So one red line is okay, one link failing, then the second link failing, third link failing, fourth link failing, and all the way 6 links fail, and then they're restoring those 6 links. And as you can see, that it's a very predictable pattern that yes, the capacity or that there is some performance degradation, the good put goes down, but that's very smooth transition from one level to the other. It keeps on decreasing as the links go down, And then eventually when the links start coming back, then it is able to leverage the additional like new capacity that is available and then operate at the highest possible throughput. So yes, this result demonstrates that VL2 is resilient to link failures. So this brings us to the end of today's lecture. And data center, when we talk about data center networks, it is all about enabling agility, right? The cost of building data center networks is very, very high. So it is very important that we increase the data center capacity in as cost-effective manner as possible, which requires us to enable agility where we can run any service on any server anywhere in the data center. And the previous generation of data center networks were not able to provide this type of agility. VL2, which was a new design or a new system that was designed by Microsoft, enables this agility and it ends this vicious cycle of oversubscription, right? So there is no oversubscription in the network. It embraces the clause topology to avoid any type of oversubscription. The results have near perfect scaling properties. It definitely helps increase the service developer productivity, but that now they can work with this simpler big switch abstraction. They can assume that all the servers are just plugged into one huge Ethernet switch. Don't worry about the topology at all. It definitely lowers the cost. High scale server pooling is possible. We can isolate tenant performance as we were looking earlier. That when you can look at it the service level isolation or the tenant level, that different services can be owned by different tenants. It leverages all the commodity networking components that are available right now and does not require using specialized vendors to build switches for you or routers for you. You can just use commodity resources. It is able to achieve high performance and reliability. So it gives the prototype that they built. It behaves as the theory predicts, which is a huge sign of relief that it's a good demonstration that something that makes sense theoretically also works in practice and helps build systems that are enabling the agility that is desired for data center network. All right, so with that we will end this lecture and I'll post this video over YouTube soon.